Hello, I am Aliette Chenal and I'm doing a PhD with a CNES at Mercator Ocean in France. My work focuses on improving sea ice thickness estimates by assimilating Cryosat-2radar Freeboard data. Today, I will present the first results of my PhD. The objective is to develop a multi-data and multivariate sea ice analysis in our assimilation system for operational purposes. I am using a new model configuration, NEMO 4.2 and SI-Cube, and I will start by showing its capacities in reproducing the sea ice cover. Then I will present the first results obtained with the experiments assimilating radar freeboard. These first experiments were done with the previous model configuration, NEMO 3.6 and NEM 3. I will finish with a conclusion and some perspectives. The model I use is a coupled one between the ocean, with NEMO 4.2, and the sea ice, with SI-Cube. This new model has been released in March 2022. I use a global grid with a quarter of a degree resolution, and my simulations use ERA 5 for the atmospheric forcing. The results are analyzed by comparison with satellite measurements and in-situ measurements. For sea ice concentration, we use the UMETSAT product. This is a passive microwave sea ice concentration product, which is already assimilated in the real-time operational model. Sea ice thickness is derived from the radar freeboard measurements. Freeboard, as explained on this diagram, is the difference between the ocean level and the tip of the ice. It can be expressed as a linear combination of sea ice thickness and snow depth, as written here. Therefore, to obtain sea ice thickness from radar freeboard measurements, one needs to know the snow depth. We use an altimetric snow depth product called ASD-KU, which computes the difference between CryoSat-2 KU band measurements, reflected by the sea ice, and several Alti-KA measurements, reflected by the top of the snow. It is important to keep in mind that these measurements don't have the same spatial and temporal resolution. For example, Cryosat-2radar Freeboard measurements are available only in winter. I will now present a short overview of the results we obtained in both hemispheres with this model configuration. Results presented here are from experiments performed without any assimilation. Experiments are performed over the 2011 to 2020 period, and I present here results averaged over this period. Sea ice concentration, represented here in the Arctic, is in good agreement with the different satellite measurements. This map here shows the sea ice concentration difference between the model and the OCSF product at the end of winter in March and at the end of summer in September. The model shows a slight overestimation of 10% of sea ice concentration during winter in the marginal ice zone. And as you can see, it presents important regional biases during summer, which result in a mean underestimation of sea ice concentration. As for snow depth here, the model has a 27% excess of snow during winter compared to the ASD snow product, and the spatial distribution of the modeled snow differs from the ASD product. The model misses the accumulation of snow northern of Canada. Sea ice thickness now, still in the Arctic, is compared to the satellite CryoSat-2 data. This figure here shows the evolution of the mean sea ice thickness. In winter, the model reflects correctly the observations. The observations are represented by the green plus signs, and the model is in plain orange line. On this side of the slide, these are maps of the March monthly mean. It shows that at the end of winter, there are regional biases. The ice is too thin in the north of Canada and Greenland, and too thick in the East Siberian seas compared to the observations. The biases actually compensate each other so that the mean sea ice thickness is in good agreement with the observation, as previously seen on this figure. Here I present a comparison with different in-situ measurements. The first row of diagrams shows the observations on the x-axis and their model equivalent on the y-axis. The color of the points refers to the latitude of the point. On the second row, you can see the positions of these points on the Arctic map. And on the maps, the color of the points shows the difference between the model and the observations. The in-situ observations of the first column here are from the USAB DG campaign. These are sea ice draft measurements from submarines, sea ice draft being the height of the ice under the sea level. The second column here represents airborne observations from the AEM campaign. It takes radar altimetric measurements of the total sea ice plus snow thickness. The model is in quite good agreement with these two datasets. Some points are a little underestimated, but the shape of the clouds generally follows the x equals y line. On the third column now here, I present a comparison with measurements of the sea ice thickness from the IceBridge QL campaign. The Operation IceBridge takes airborne measurements with radar altimetric techniques. Here, the points clearly shows that the model underestimates the thicker ice on this side. The maps point out that this thick ice is located in the north of Canada and Greenland. To summarize, the comparison with the in-situ data highlights the same characteristics of the model that we noticed when comparing to the satellite data. The model sea ice is in agreement with the observations, but it is too thin in the north of Canada and Greenland. Now let's look at the results of the simulation in Antarctica. The first two figures here shows the sea ice concentration difference between the model and the OCSAF product at the end of summer in March and at the end of winter in September. The model largely overestimates the ice during summer. It amounts to 109% more than what's been observed with the OCSAF product. In winter, the model also showcases an overestimation in the marginal ice zone of 21% sea ice concentration. Regarding snow depths here, the model also greatly overestimates the amount of snow, with a 67% excess of snow during winter, compared to the ASD snow product. Sea ice thickness in Antarctica is shown here. The first diagram here presents the temporal evolution of the mean sea ice thickness. The ice is way thinner in the model during winter. The observations are represented by the group plus sign, and they are all half a meter above the NEMO 4.2 NSIQ model in plain orange line. On this side of the slides, these are maps of the September monthly mean of sea ice thickness. The ice isn't thick enough in the thicker regions compared to the satellite measurements. I am still trying to find the best parameters possible for the NEMO 4.2 NSIQ model in terms of different sea ice and snow parameters in order to correct the sea ice variables, especially in the south. However, the purpose of my work is to apply a constraint on these variables through data assimilation. An assimilation system, therefore, was set up as a test on the previous model configuration, NEMO 3.6 coupled to the sea ice model LIM3. The data assimilation runs with a singular evolutive Kalman filter on a 7-day cycle. It includes an ocean analysis, explained here, and a sea ice analysis explained in this blue box. Sea ice concentration from the OCSAF product is already assimilated in the operation model. We are now adding assimilation of radar freeboard measurements here in order to better control the sea ice volume. I will now present the first results of the assimilation experiments with the NEMO 3.6 and LIM3 model and a sea ice volume assimilation, which includes information from the Lagos Cryosat-2radar Freeboard and from the snow depth climatology Warren 99. In the future, this assimilation system needs to be adapted to the new NEMO 4.2 NSIQ model, and we plan to use the ASD snow product from Lagos for data assimilation. On this slide, you can see the results of the assimilation in the Arctic for a 3-month run between January and March 2011. The first column here presents the resulting maps of the model sea ice volume, with figure 1A for the free run without any assimilation, and 1B for the run with assimilation. Both maps present realistic sea ice volume, but the assimilation adds more small-scale patterns to the modeled sea ice. On the second column, I compare the results of the simulation to the assimilated dataset, Cryosat-2radar Freeboard. The points represented on the plots are model radar freeboard equivalent of the along tracks observations, with the observations on the x-axis and their model equivalent on the y-axis. This first plot 2A is the result of the free run without assimilation, and the plot 2B is the one with assimilation. The points of the run with assimilation are much more linear and present a better slope than the run without assimilation. And now you can see here a comparison with another dataset than the one assimilated. It is the sea ice volume project from the Alfred Wegener Institute, which uses Cryosat-2radar Freeboard, computed with different algorithms than the one from Lagos, and still around 99 snow climatology. So it is not a completely independent dataset, but it's still different. The maps present the difference between the sea ice thickness of the model and the one from the AVI product. It is striking that the assimilation corrected most biases, especially in the Beaufort Sea, in the north of Canada, and in the Siberian seas. There are still, however, a negative bias at the east of Greenland and near the Atlantic Ocean that could not be corrected by the assimilation. To summarize, we have some promising results with the assimilation of CryoSat-2 Freeboard radar experiments. It corrects a lot of the sea ice volume biases with the NEMO 3.6 and In-situ model configuration. Then the new configuration, NEMO 4.2 and SICube, produces a sea ice cover in good agreement with the different observations in the Arctic, but it still has some issues with the sea ice cover in Antarctica. We are still working to correct it thanks to parameters tuning. In the near future, we want to switch Snowdepth product for freeboard retrieval. Instead of using Warren 99 snow climatology, we will use the ASD KAKU snow product from Lagos. ASD KAKU product is available in Antarctica, while Warren 99 isn't. Hence, using ASD snow product will allow us to use data assimilation in the south, which could also help us correct some biases in the sea ice cover in Antarctica. Another challenge that will be made in the near future is that we will adapt the assimilation system to the new model configuration, NEMO 4.2 and SICube. When doing that, we plan to work with an ensemble assimilation system. It is now the end of my presentation. Thank you very much for your attention, and please do not hesitate to ask questions.
So I think Aliette's on the call. Yes, hi Aliette. Does anyone have any questions for her?
Yeah, really nice talk. I was wondering if you were doing the minimization of the sea ice thickness and the sea ice concentration separately, and if not, I was sort of wondering what you were doing in terms of the covariances there and how they were computed.
Yes, thank you for the question. I'm not sure. I think we do it separately, but I'll have to check. Because yeah, I've seen that there are like a lot of different methods for the covariances between sea ice thickness and sea ice concentration. And sorry, I'm not sure about what we do exactly.
Question.
Hi, what densities for snow and ice do you use?
We use it's a fixed density.
Thanks.
And I'll check and write in the chat what they are exactly. Sorry.
I noticed there was still some bias with assimilation north of Canada. Did you have a variable model error, or was it a fixed model error?
For the model error, we built anomalies from a previous long-term experiment, and so like it was a 10 years experiment reanalysis. And with this, we built anomalies, so like difference to the mean, to represent the model error.
Hi, I was wondering, so IceBridge, data is in March, April, all of them. The 2 other data sets you were using, what time of year are they?
I'm not so sure, I have to check. Okay, sorry.
Okay, thanks very much. I'm going to move on to the next speaker now. Thank you, Aliette.
Thank you very much.